All right, in today's lecture, we are going to solve the traveling salesman problem using Larson's heuristic. So what is a heuristic? I'm sure you've heard the word before. If you haven't, well, we'll talk about it here for a second. It's of Greek origin, as it says. It means to find or discover. A heuristic method for certain types of mathematical computational problems sometimes does get us to the optimal solution. But more often than not, it gets us close to the optimal solution. Some problems are just so complicated that to solve them, it would take a really long time, or to solve them might, maybe there isn't exactly the solution that we hope for. So I was just checking my settings here. Okay, now there are, as it says here, exact solution algorithms that do find the optimal solution to the traveling salesman problem, but as it says, they are grossly inefficient. They take a super duper long amount of time to solve. So this is Larson's, he calls it the TSP1, and we're going to make some assumptions here that when we're going from node to node, because remember, this is a node covering or atom covering problem in contrast to the Chinese postman problem, which is an edge covering problem. So we're going to assume that we have a symmetric distance matrix. That means if I go from node A to node B, it's the same distance as me going from B to A. Sometimes that's not always true, but we're going to assume it here. And we're going to assume that we can get from every node to every other node. Now, the heuristic itself is in the textbook, and it's on here, slide 3. I'm going to be following these steps, but kind of in my own terms and in my own wording, okay? So this is just what we're going to find that's actually in the textbook. And I'm going to start with a text example, and you might remember that we ended our last lecture by finding the minimum spanning tree for this 10-node network. Now, the way it's laid out here on this slide is different than the way we developed it in the previous lecture. However, it's still the same minimum spanning tree. And you might remember, let me use a colorful pen here. You might recall that the minimum spanning tree that we developed, I know it's hard to see these nodes here, it goes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then the minimum spanning tree here, maybe it's miles or kilometers, I'll leave the units off in this case. We started at node 1. And then we visited every node, or we started our minimum spanning tree at node 1, and we ended up with this when we started the algorithm, and the length ended up being 258. And then in the previous lecture, I also started again, or suggested that you start at a different node. I happen to start at 7. You're going to get exactly the same distance, but I also got the same minimum spanning tree, because it's possible to have more than one minimum spanning tree that has the same total distance. So the way Larson's TSP1 works is as follows, and I'm just going to write this down because I'm going to be following these steps here. This is the TSP1 heuristic. So the first step says to find a minimum spanning tree of your network. So find a minimum spanning tree. And as I said, we did here, and it happens to be equal to, so the length of my minimum spanning tree is 258. Okay, now step 2 says, we're going to make a list of all of our odd-degreed nodes. This is the step that's a little bit complicated and hard to understand when you first read it in the textbook, so I hope to bring some clarity to this. So first we're going to make a list of my odd-degreed nodes. So I'm just going to put them up here. So my odd nodes, those are the ones where we have, odd degree. So for example, node 1 is of even degree because it has 2 arcs coming out of it. Node 2 is of odd degree because it has 3 coming out of it, so that's my first list there. How about node 3? Node 3 only has 1 in the tree, so that's added to my list. Node 4 is also an odd degreed node. How about 5? 5 is not. 5 has 2 arcs, so it's not in my list. 6 is an odd degree. And then let's see, how about 7? 7 has 3. I think you might be able to hear my cat crunching on the cat food, and I apologize, but she's on hospice care right now at home, so I'm letting her eat whatever she wants. 7, and then 8 is of even degree, 9 is of even degree, 10 is of odd degree. So these are all of my odd degree nodes. Now here's where it gets a little bit funky. It says, make a list of the, find the minimum path pairwise matching, and then we're going to add the links of that minimum pairwise matching to the graph. Now this gets a little bit hairy, so I'm going to do it all over the sheet so you can see what I'm doing, but this is what we mean by the minimum path pairwise matching, and I'm going to do these all in different colors. So I'm going to start with purple. So I'm going to take there's 3 pairs here, and I'm going to add up the minimum distances for each of those. All right, so let's start with the simplest pairing, and this is the way I've been doing it. I'm kind of keeping them in pods here. So I've got a square or a rectangle here, and I've got my pairwise matching. So we have 2 to 3, and then 4 to, wait a minute, where am I here? 2 to 3, 4 and 6, and then 7 and 10. So I just took them kind of in order here. And then on the bottom here, this is going to represent the total. So in going from node 2 to node 3, the distance there is 29 units. You can read it from my from to matrix here. So 2 to 3 is 29. Then 4 to 6, and notice this is symmetric, so 4 to 6 is the same as 6 to 4. So 4 to 6 is 71, and 7 to 10 ends up being 43. So when I add all of these up, 29 plus 71 plus 43, I end up with 143. So that's one of the ways that I can do a pairwise matching. Now let me continue with 2 and 3 here. We could also do, we can have, let me find my notes here so I don't screw this up. 2, 3. Then we can have 4 paired with 10, which will leave 6 paired with 7. Now, when I add these up, I'm going to have 29. 4 to 10 is 108. And 6 to 7 is 40. And when I add those all up, I get 177. So I'm going to continue to do this for as many of these pairwise matchings as I can do. There's one more that I can do here. That was 177, right? 4 and 10, right? Now here's another one. We've got 2, 3. Let me make my block here. This is going to be a very cluttered slide, but I think it's important to have it all here so you can see it. So we can have 2 to 3, and then the other matching that I can do here is 4 and 7, and then 6 and 10. And if you catch an error, by the way, let me know. But I have this pre-prepared. So if you catch an error, let me know. 2 to 3, still 29. 4 to 7, though, now is 71 again. Is that right? 4 to 7. Yeah, there's 2 71s in there. And then 6 to 10 is 46. So adding these up, we should get 146. So that's one set of pairwise matching. Now let's do another pairwise match. Let's go and start with 3 and 4 here and see what we get there. And I will use a orange pen for contrast there. I'll kind of do it down the side here. So let's do, we have 3 and 4. And then we can also we'll have 3, 4, then I'll do 2, 6, and then I'll do 7, 10. 3, 4, 2, 6, 7, 10. And hopefully I read these right. We had 3 to 4 is 52, plus 2 to 6 is 68, plus 7 to 10 is 43, for a total of 163. And then I'm going to continue with this, and I'm just going to, I'm running out of space here. Hang on. Then we'll do 3, 4 again. And we'll have 3, 4, let's go 2, 7. And then that will have 6, 10 as my last one. Whoops, with the total. And that will be again 52 plus 2 to 7 is 49, plus 6 to 10 is 46. And when I add those up, that's 147. And then we have one more here with the 3, 4. So we have 3, 4. And then we'll have 6, 7. And then 2 to 10, and that will be 52 plus 6 to 7 is 40, plus 2 to 10 is 91, and that is 183. So that's all the ways I can match starting with 3, 4. Now when you keep doing this, you end up kind of double dipping, and I'll show you what I mean by that. But let's move on to, let's go to the pair 4, 6. All right, and for 4, 6, let's use a blue marker. Okay, so we'll do, let me see, do I have room? Let's just do it right here. So we'll go right here. We can have 4 and 6, and then we can have 2 and 3, 7 and 10. So 4 to 6 will be 71, plus 2 to 3, which is 29, plus 43, 7 to 10, and that will be 143. Well, look what I just did. This is what I mean by double dipping. This here, I'm just going to highlight it in yellow, is exactly what I originally did up here. So that's what I'm saying by sometimes when you start doing this complete enumeration, and there's something called a matching algorithm that you could employ, and there would certainly be software, you could write a program for it, but you might end up just doing the same thing twice, and so that's an example of doing the same thing twice. However, when I look at the other matchings that start with 4 and 6, I don't think I hit another one. Let's see here. We have 4 and 6. Then the next one, we could have 2 and 7, which leaves 3 and 10 left. And then I'll have 71 plus 49 plus 114. That's a 7 right there. And that works out to be pretty high, 234. And then my last one that I can do, starting with 4 and 6. You'll get the hang of this after you do a few of them. We would have 4, 6, and then we have 3 and 7, and then 2 and 10. So that will be 71 plus 72 plus 91, and that total will be, oh, it works out to be the same, 234 right there. And now I think I'm down to I'm almost done here. Hang on. Got 2 more sets to do. Let's go with this pretty purple color. And let's go with, it probably looks like the orange there. I know that there's going to be 3, so I'm just drawing ahead here. All right, so the next pairing then, I'm going to go with 7 and 10. So each one of these will start with 7 and 10. So the first, we can have 7, 10, and then we can have 2, 3, and then we can have 4, 6. Well, do we already have one of these? Look, we do. So I was wrong. So 7, 10, 2, 3, 4, 6, 7, 10, 2, 3, 4, 6. I already know what that's going to be. That's going to be 143. So I've just triple dipped here. Still the same as that one. By the way, it happens to be the minimum, and by the way, this is going to be the answer to this slide eventually. But let's look at the other ones. We can have 7, 10, 2, 6, 2, 6, and then 3, 4. So what does that end up being? 7, 10, 2, 6, 3, 4. So 7, 10 is going to be 43. 2, 6. Oh, shoot, I'm going the wrong one. Sorry. 7, 10 is 43. Well, I might as well fill this one out, right? Why not? 43. 2, 3 is 29, and 4, 6 is 71. I might as well fill that out. So 7, 10 is 43. 2 to 6 is 68. 3 to 4 is 52. And when I add those all up, I get 163. And then I have 7, 10 again is 43. Then my next pairing, make sure I'm following my notes here. Then we'll have 2 and 4. And then we'll have 3 and 6. So 2 to 4 is 34, and 3 to 6 is 96. And hopefully when I add all those up, I get 173. I'm down to my last 3 now. We're gonna, my next pairing will be, what did I screw up here? Oh, I jumped the gun a little bit. I should have done 6, 7. The way I was doing this, I had a pattern, and then I kind of messed it up, but that's okay. I just messed up the pattern. So my next, the last pairing that I can do is gonna start with 6, 7. So let me make my 3 boxes here. So we'll have 6, 7. All right, and then, so we'll have 6, 7. Then we can have 2, 3, and 4, 10. Which I believe is also a duplicate, but I'll write it down anyway. 6, 7. Yep, right here. It's the duplicate is right here. So we have 6, 7 is 40, plus 2 to 3 is 29, plus 4 to 10 is 108, and that's 177. And I don't have a good highlighter there, but I'm going to use an arrow here. So that one is a match to that. Then we have 6, 7. And then we have 2, 4, and 3, 10. So we have 40 plus 2 to 4 is 34. 3 to 10 is 114. That gets me 188. And then we have 6, 7, then we'll have 3, 4, and then we'll have 2, 10. Does that match also? I don't, let's see, 6, 7, we have a 2, 4, 3, 10. How about, well, I think this one might match. Do we have a 3, 4 here somewhere? We have 3, 4, yeah we do. 3, 4, 6, 7, and 2, 10. So I know this is going to be 183 because this one matches this guy right here. But let's just verify it. 6, 7 is 40. 3, 4 is 52. And 210 is 91. So we've got another pairings here. Okay, we've actually exhausted everything that we can do here as far as I can tell. Now, let's go to the second sentence here. First, we find the minimum path pairwise matching. So the minimum is in yellow, all right? It's any of these three that we identified, and they're all identical, right? So this is the minimum path pairwise matching. Why is it minimum? Because it's the lowest of all of these totals that we've got. 143 is the very lowest that I can get. Now what it tells me to do is to add the length of this, the lengths of the minimum pairwise matching to the graph. So I'm going to do that in red. So I'm going to add 2 to 3. Let me just move this over here. 2 to 3. So that's going to be a separate link. We know it's going to be 29 here. So that's 29. And then, what's the next one? 4 to 6. So that's going to be right here, like so. And 4 to 6, that is 71 units. And then we're going to add 7 to 10, which is, what is it, 43 units right here, right here. So that is step 2. Now what is step 3? It says, take this, and what we're going to do is get an Eulerian tour on the graph, beginning and ending at the start node desired by the TSP. So in this TSP, we're actually starting at node 10 in this case. They were going from 10, and we're going to start at 10 and go all the way. I don't know why they didn't start with 1 over here, but that's fine. So here we have step 3. Now what I have to do is I have to just draw those links back in, okay, to continue with the algorithm. So we have a 29 here, and then we have a 71 here, and then a 43 here. Okay, so now it says draw the tour, starting and ending. So we want to start at 10, and we can get a tour as follows. There's a couple of them actually. So here's one tour, T-O-U-R. We can go 10, 9, 8, 7. I'll start it out here. We can go 10, 9, 8, 7. 1, 2, 3, 2, 4. 1, 2, 3, 2, 4. 6, 5, 7, 10. Okay, that's one tour. Here's another. So another tour, Eulerian tour we can do will be, we can go 10, 7. We'll start that way. 10, 7. 1, 2, 3, 2, 4. 6, 5. Yep, sorry. 6, 5, 7, 8, 9, 10. Now both of these tours have a length equal to the MST length plus the minimum pairwise matching that we did from the previous slide. So here, both of these tours will have, it was 258, that was my MST, plus the 143 from the previous slide. So both of these tours have a length that is 401 units. Now this is not the optimal, this is just part of the algorithm. We're still not done with the algorithm. Notice that we have visited nodes or atoms 2, and 7 are visited greater than 1 time. So remember, a traveling salesman problem wants us to hit each node at least once, but in minimum distance. So if we can't do it exactly once, we want to do it as few times as possible. So for this particular solution, 2 and 7 are both visited more than 1 time. And that brings us to step 4 here. And this is where, let me see here, how do I do this? Well, let's do it this way. So here's step 4. I still have to redraw on it. Let me write down what, I want to write those tours down one more time so you can see what they were. So again, the tours were 10, 9, 8, 7, 1, 2, 3, 10, 9, 8, 7, 1, 2, 3, 2. Remember there were these extra arcs here. All right, 1, 2, 3, 2, 4, 6, 5, 7, 10. And then the other one, as I said, or we could go 10, 7, 1, 2, 3, 2, 4, 10, 7, 1, 2, 3, 2, 4, 6, 5, 7, 8, 9, 10. Okay, so in this step, we're going to take a look and use something called the triangle inequality. So here's an example of the triangular inequality, okay? So this, I'll write it over here, triangle. So you could look at this step as an improvement step. So remember, right now we've got 401 total, right? Now notice, if we go, I'm going to use, let's use this tour right here as my example, all right? Notice, if we go 8, 7, 1, okay? So 8 to 7 to 1, so I'm going to kind of highlight that right here. Just by looking at this tour, let's do the top tour, okay? That is going to be 31 plus 29 equals 60 units, right? Well, 7 is visited more than once. So remember that we have nodes 2 and 7 are visited more than 1 time. So we're going to look at each of these nodes for this triangular inequality. So 8, 7, 1 is 60. What if, because 7's already visited, you know, a few times here, at least twice, right? So what if we just went, but if I go directly, 8 to 1 is just the distance from 8 to 1. So 8 to 1 is 41 units. So I can save 19 units there by taking out, by instead of going 8 to 7 to 1, I could just go 8 directly to 1. So that's one improvement. I'm going to put a bullet there. And here's another improvement. If we go over to node 2, which is visited several times, if I go 1 to 2 to 3, so 1 to 2 to 3 is 25 plus 29, and that is 54 units. So let me highlight that. So here again, again, now we're going to go 1 to 2 to 3. But what if I just went directly from 1 to 3? So, but 1 to 3 is 43 units. So I can save another 11 units right there. So now what I can do is I can improve on my tour in step 4 by shaving off some of this. So I can improve, so I'm going to write this, improved TSP1 heuristic solution, because it's not necessarily optimal. I'm going to show you that it's not optimal. Improved TSP1 heuristic solution is as follows. We'll go 10, 9, 8, 1, 3, 2, 4, 6, 5, 7, 8, 9, 10. Now, if you do this, it should work out to be 371. Now remember, we started with 401 units. Then we used the triangular inequality. We were able to shave off, we have 19 here and 11, which is 30. So 401 minus 30 gets me 371. And now I want to show the best tour. How can I do this that will work out? Oh man, yellow. I don't want to use yellow. Let's use a color. Oh, let's just use black. I mean, what the heck, right? Let me use black. That's not going to contrast either. Let's use orange. Okay. So let's show the heuristic solution. So we would go 10 to 9, so that'll be 36. Then to 8, 47, right? I'm just going to keep a running total here just for myself here. We'll have 36 plus 11 is 47. Then we're going to go to 1. You see, it wasn't even part of this spanning tree, right? But now we're going to add this back in. So 8 to 1, that was 41. So 47 and 41 makes 88 at that point. Then we're going to go to 3, right there. And we know that that's 43. So that's going to get me, 43 is 131. I'm just doing a running total here. Then I'm going to go to 2, which is 29. So 29 gets me up to 160. Is that right? Yes. Then I'm going to go to 4. Maybe I should put some arrows on these. Let's do that. Let's put some arrows here. Yeah, I like that better. So 2 to 4, that's another 34. So that gets me to 194. Then I'm going to go all the way over to 6 here. In a second, I'm just reorganizing here. Sorry. So what does that get me? That gets me 71. So that gets me up to, I believe that makes me up to 265. Let me double check that one. Yep. And then we go to 5 for 27 units there. And so adding 27 units gets me to 282. Then we'll go over here to 7 for 36 units. And that will get me to 318. Then we're going to go to 8. Wait, am I doing this right? 7 to... What have I just done? 10, 9, 8, What have I just done? Oop, got to correct a couple mistakes here. This is 292 right here. This is what I get for working without a net, right? So we have, when we get to node 5, we have 292, and also we don't go back to node 8 here. So I made a bit of an error here. We wouldn't go 7 to 8 to 9 to 10. We're going to go 7 directly to 10. I accidentally threw, I don't know what I was doing here, but I screwed that up. Sorry about that. So here's my tour. Here's where I made my improvements. We still went 6, 5, 7, 10. So it should go 6, 5, 7, 10 here. So when we were sitting here at node 5, so when we're sitting here at node 5, then we're going to go 36 units to 7. So that should be 328, not 318. And then we go 7 to 10, which is 43. And then when we add the 43 there, that's how we get to that 371 right there. So in orange, this is my TSP heuristic solution for 371. Now, the actual optimal solution is 331. So this is the actual optimal solution right here. So this is the optimal TSP. If we had solved it using the algorithm that would get us to optimal, but instead we were using Larson's heuristic, as I said. So how is this one different from what we did? Oh, by the way, the optimal TSP is, it has a length of 331. So if you add this up, so how does it differ from the one that we just did? Let's see here. This is the one that we just did. I don't know if I can keep them all on the same, well, kind of here. Let's see. So it's pretty much the same. We go 10 to 9 to 11, or I'm sorry, to 8. And then instead of crossing over here, it reinstates going back from 8 to 7. Then we'll go 1 to 3 to 2. Where is it? Oh, I see where they say. Here's where they save it. See where this 71 is here? This is where the optimal saves some of the distance. So then we go 2 to 4, which is 34. So far we see that we have a little bit of a difference here between my heuristic solution in orange and my purple here. Then instead of going from 4 to 6 like we did in the heuristic, we're going to go 4. I don't know if you can see this, 4 to 5 to 6. Which is actually more than 71, but in other words, you sacrifice a little bit here to get a bigger benefit there. And anyways, this is the traveling salesman problem optimal solution. There's no way you can get a smaller value than 331. I think these are like super fun to do. So the next slide is for you to try one. And I'm going to encourage you to do that. The actual answer is on the next page. So rather than me do it here in the lecture, I'm going to recommend that you stop the tape, go back, and then follow the algorithm and see if you can get on slide 10 the answer that that I actually got when I did it. And you should, let me see what I want to say here. I don't really have anything more to add, but see if you can get that. It'll be good practice. Okay, thanks folks. Have a good day.